Actually, maikli lang naman siya since we only have two subtopics for this one, same as Module 4. So for Module 5, we have the foundations of quantum mechanics. Hindi pa rin tayo makasimula ng quantum mechanics. Ang foundation pa din pala siya. Now, we have the wave nature of electrons and then the uncertainty principle. So um, uh, coming from the previous lectures class, we know that light is considered as wave, and according to the photoelectric effect, we also consider light coming as particles with energies coming in also in packets of energies. We have energy is equal to h nu. Um, I mean increments of energy equal to h nu. The foundation of quantum mechanics class is we would be for this module we would be discussing this duality principle being applied to electrons. Okay, and then we'll be getting the we have to answer the question that we were left with, the I mean shortcomings coming from the atomic theory of Bohr, which says that spectral lines um, by calculation could not be like described perfectly in I mean series of experiments. Have could it be like could we know for certain that these lines would just be fine lines along the electromagnetic spectrum, or could we have um, huge wavelength or broadness spectrum or not? So we'll be discussing all those things. So let's start with the foundations of quantum mechanics. So it became clear in the class that the Bohr theory was inadequate and that a completely new approach was needed. So Bohr himself again helped to point the way through his correspondence principle. So nung i-exit na sa eksena si Bohr, syempre nag-conclude siya. And ang conclusion niya is correspondence principle, which states that any quantum theory must reduce to the familiar classical laws under the conditions for which classical behavior is expected. So ang sabi niya, same lang din class with Planck's, what we call this? Planck's, what we could derive from Planck's statement, that we have this uh, classical view na hindi natin dapat kakalimutan, no, but these um, quantum mechanics would become classical mechanics pa din if I mean if um, the how would we say that? So if yung ating conditions ayan would make these contributions of quantum treatments negligible. Yan. So, babalik pa din tayo sa classical behavior as expected. And then kapag nasa classical behavior na class, mag-govern pa din lahat ng classical laws natin at hindi siya, alam niyo yun, galing sa quantum mechanics, mag-violate na siya ng classical behavior kapag nasa macroscopic world na. So, govern pa din siya ng classical mechanics. So the first positive suggestion for a new approach to the problem was made by the German physicist Max Born. His paper appeared in 1924 with the title Zur Quantum Mechanik. This is the first time the term quantum mechanics had been used. So si Max Born class ang what do you call this? Senior ni Werner Heisenberg. Siya yung advisor, yan, parang gano'n, ni Werner Heisenberg, assistant, yan. So sa isang research lab, if you're going to apply for I mean to work in a lab class, meron kayong mga project leaders, and then you'll be doing projects under their name. So you'll be subjecting yourselves into them, submit everything into to them. So i-check naman nila lahat. So for this one, in the spring of 1925, Werner Heisenberg developed the first satisfactory system of quantum mechanics, at ang ginamit niya for this one class is matrix. So it involves matrix mechanics na during that time, walang kalam-alam si Heisenberg na meron ng studies regarding sa matrix mechanics. Actually, class, sa atin kasi, tinatamad pa nga ang marami sa atin to look for related literatures. But then, we have already almost everything. I mean, everything na, we have almost everything ano, sa internet regarding these would be related literatures sa mga trabaho natin. But for, of course, during their time, medyo mahirap yung gawin. Actually, class, what happened is, gumawa ng matrix mechanics si Heisenberg from scratch. And, kumbaga, he reinvented matrix mechanics. Isipin niyo, 20 years old, nakapagpasa na siya ng published paper na kinilala ng physics community during his time. Tapos ngayon, gumawa siya nag-reinvent siya ng matrix mechanics. How was that, diba? So, sobrang husay ni Heisenberg for this one. Pero class, yung nagawa ni Heisenberg na what do you call this? Na system para sa quantum mechanics is something na sobrang complicated na kumbaga kaya naman siyang intindihin in a sense pero hindi siya ganun ka kabilis i-digest for many people, especially for yung mga physicists na bago pa lang sa quantum net, and then yung mga chemists natin. So ang ginawa ni Born during that time, actually binasa niya yung work ni Heisenberg, and kahit siya ay sobrang nahirapan sa panahon niya. So ginawa nila is gumawa sila ng panibagong way para medyo mas mapadali siya. So, noong 1925, si Paul Dirac, ay nakatanggap ng Nobel Prize in Physics the same year na nakatanggap si Heisenberg. Si Dirac at si Schrödinger, sila ay naghati sa, if I'm not mistaken, naghati sila sa 1933 Nobel Prize in Physics. Yun din yung time na natanggap ni Heisenberg yung kanyang Nobel Prize. Pero yung work niya is for 1930. So tatlo sila nakatanggap ng year na yun. Correct yun na lang ako kung mali. So based on, he developed a similar system of quantum mechanics based on Hamilton's method of classical mechanics, which he transformed by means of postulates into a very versatile system of quantum mechanics. Since class, this is a brand new branch of physics or brand new branch of science. Nagsisimula lang lahat ng mathematical expression nila coming from their postulates. So what they would do is they would be writing postulates, and then after nilang ma-establish lahat ng gusto nilang sabihin sa postulates, itatranscribe nila yun into mathematical expression. So actually yun din yung ginawa ni Heisenberg, kaya nga lang gumamit kasi siya ng matrix, which is sobrang hirap naman. Kumbaga, actually hindi naman mahirap class ang matrix. Actually, mas straightforward nga ang matrix. Ang kaya nga lang class is mahirap i-describe ang matrix. So, ang kailangan is more on yung straightforward na equation na kaya nating i-describe. No? So, shortly afterwards, the Austrian physicist Erwin Schrödinger developed what appeared at first sight to be an entirely new system of quantum mechanics, in which, because of its use of familiar concepts related to waves, was much easier for chemists to understand than the system of Heisenberg and Dirac. Pero during this time class, syempre, objections were made against the work of Erwin Schrödinger, but he tried to actually he came up with a plan na mathematically i-deduce niya yung ginawa ni Dirac and yung ginawa ni Heisenberg using his work. So, yung ginawa ni Schrödinger is in-equate niya, nag-derive niya yung ginawa ni Paul Dirac at yung ginawa ni Werner Heisenberg galing dun sa kanyang sariling trabaho. So, actually class, what happened is, pare-parehas lang naman actually sila ng nagawa, pare-parehas actually ng postulates. Magkakaiba lang syempre ng way kung paano dinescribe yung postulate or in-structurize yung postulate. Pero pare-parehas sila ng math. Okay, so magkakaiba lang sila class ng way ng pagsisimula ng math, pero eventually, they found out na pare-parehas lang naman talaga yung ginawa nila. So deserve naman nila lahat ng binigay sa kanilang Nobel Prize. in physics. Anyways, babalik tayo class kay Schrodinger ha. Yung mismong equation ng Schrodinger pero sa module 6 na yun. So for this one, discuss lang natin yung naging basis ng theory ni Schrodinger. At yung naging basis niya class is somewhat simple na yung ating electrons ay i-consider lang natin siya as wave. Same way na kinonsider natin na particle ang light. Gets? So kung ang light ay may particle wave duality, according to Schrodinger's theory, ang electrons din could also have that duality. Okay? So it is often referred to as the wave mechanics rather than quantum mechanics, and was based on the realization that elementary particles such as electrons have wave properties just as radiation has particle properties. So kung ang radiation class pwede mong i-describe as a wave and describe as a particle, ganun din ang electron. So meron din tayong wave nature for electrons, and so pwede natin siyang i-describe using mathematical expression for waves. Get it? So yung module 1 natin siya. So ganun lang din ulit yung gagawin natin. Another phenomenon supporting this is what we call the Compton effect. Actually, class, yung reason kung bakit sila nag-come up with having the duality principle for light is because of the black body radiation. That's one. And then the photoelectric effect. Right? So sa dalawang yun, they found out na indeed light has this duality in nature. And also they have this Compton effect. What is the Compton effect, class? This is another, again, phenomenon that support the duality of light, which is a work by the American physicist Arthur Holly Compton, who investigated the scattering of monochromatic X-rays by a target such as a piece of graphite. So ang ginawa niya, class, is as simple as this one. Pinatamaan niya yung graphite ng isang beam ng X-ray. Tapos tiningnan niya, class, yung lumabas na wave. At he found out that there are actually two waves. Yung isang wave, class, has the initial wavelength same nung ating X-ray, nung incident X-ray. And then the other wave, class, is is a ray which has a lower energy than the incident ray. Get it? So, ang reason lang, class, dito is this one. So, dito sa figure, if you could see, may incoming high energy photon, and then yung photon na yun ay tumama sa isang electron, and then yung electron, class, ay natanggal. Diba sa photoelectric effect, yung electrons yung tinitingnan natin? Right? So, dito, class, ang nangyari is, yung electrons ay natanggal, and then, since high energy to, meron pa ding lumabas na resulting ray. Got it? At yung resulting ray natin, class, has a lower energy or a higher wavelength. So by the virtue, class, of energy conservation, he found out na he concluded na yung ating yung ating photons actually ay nababawasan siya in energy. So meron siyang duality in nature na isa din siyang wave pero at the same time isa din siyang particle. Gets natin? So yun yung nangyari sa Compton effect. So by the virtue of Compton effect and again the black body radiation observations and the photoelectric effect, nag-come up sila sa duality principle. The one in particular who hypothesized the duality of matter, the duality of in nature of matter is Louis Broglie. So Louis Broglie, who suggested in 1924 the converse hypothesis that particles such as electrons can also have wave properties, or the wave particle duality of nature, so of matter. What happened? Yeah, to obtain the wavelength of the wave associated with a particle of mass m moving with speed u, de Broglie reasoned as follows. Ang sabi niya, according to the special theory of relativity by Einstein, energy class could be equated to the mass and the momentum of the light. Tama ba? So we have E is equal to PC. Also, pwede din natin, class, na equate according to the special relativity of Einstein, we have energy could also be related to the speed of light and the mass. Okay, so we have E is equal to mc squared. Got it? So the relative rest mass of the photon, class, is 0. Yan yung totoo para sa photon. Pero hindi siya totoo, class, for other entities. Like for example, for electrons, kasi meron talaga silang mass. So E is equal to PC, which is equal to P times the, alam natin, class, that C is just your wavelength times frequency. So P times wavelength times frequency. Class, pwede makahingi kahit 5 minutes. Okay lang. Mag-OT ng 5 minutes. And then we have the wavelength. Wavelength class is equal to the Planck's constant divided by the momentum. Tama ba? Kasi actually class, momentum is just the Planck's constant is just equal to momentum times wavelength. Tama ba? So extracting wavelength, so what we'll be getting is h over momentum. This expression is for the electromagnetic radiation, and de Broglie suggested that a parallel expression would be applied to a beam of particles of momentum p and velocity u with a mass m. So ang sabi niya is wavelength is just equal to kung sa light we have h over p. So kung titingnan naman natin siya in in electrons or other beam of particles, we have h over mu. Got it? So this wavelength is of magnitude similar to the distance between neighboring atoms or ions in a crystal, and it was therefore suggested that a beam of electrons could be diffracted by using a crystal as a diffracting reagent. Actually, great thing. So actually, class, this is very much this is of high importance class in crystallography. If you are familiar with X-ray diffraction, so kapag meron kang X-rays, pinatama mo siya sa for example, thin natin na foil ng isang thin na crystal natin. So pag tumama siya doon, magkakaroon tayo ng diffracted na rays. Right? So yung diffracted natin na rays class would give us the distance between crystal lattices. So yun yung reason kung bakit napaka-importante ng X-ray diffraction sa crystallography. So, pero syempre hindi naman yung kasama sa discussion natin sa PChem. Pinakita ko lang na ito yung reason kung bakit pininiwalaan na sa X-ray diffraction class, you would get the distance from one lattice to another lattice by just checking the incident, the diffraction incident, the angle of diffraction of the incident high energy X-ray. Okay. So the realization that electrons have wave properties leads at once to an interpretation of Bohr's hypothesis of stationary orbits. Ang sabi class ni Bohr, paikot lang ang electrons, right? But then, since napatunayan nga na wave din ng electrons or tinanggap na wave ang electrons, ito talaga yung dapat niya na itsura. So we have here this figure. So the de Broglie wave associated with an electron in a Bohr orbit of radius r, if the circumference is 2 pi r, is equal to an integer n multiplied by the wavelength lambda, the wave will fit into the orbit an integral number of times and constructive interference will occur. Class, ito lang yung possible ha, yung figure A natin, 11.9a. Hindi pwede yung figure B. All because kailangan class yung ating yung energy state natin is stable enough. So ibig sabihin at meron siyang increment lang yung value ng energy. Meaning class dapat continuous yung magiging ikot ng ating wave, yung amplitude ng wave natin at magkakaroon class tayo ng interference. Kasi class, if you would consider itong letter B, this is also a possible scenario, right? Kung yung ating circumference ng ating circle is not equal to n times lambda. Get it? So ibig sabihin, kung hindi siya equal to n times lambda, hindi nagtatama yung mga amplitudes natin. There would be no interference. You got it? So para magkaroon tayo ng allowed na interference, kailangan class, equal siya sa isang integer. At yung integer natin is what we call the principal quantum number. Okay? So again, there's no such thing as 0.5 na or 0.75 kaya na principal quantum number, laging 1, 2, 3, 4, and so on and so forth lang. So we have 2 pi r is equal to n times lambda. So ito yung dapat natin na masunod. So we have the circumference equal to n, which is the principal quantum number na allowed lang, times the wavelength. Okay? So we have 2 pi r is equal to n times h over mu, plus galing ito dun sa ating expression for wavelength sa de Broglie principle, sa de Broglie duality principle natin. So we have h over mu. And then, of course, after checking, we have MUR, which is the angular momentum natin, equal to nh over 2 pi, or nh bar. Okay, so this quantity MUR is the orbital angular momentum, kung makikita nyo kanina, which Bohr had postulated to be an integral number of h over 2 pi. Actually, class, tama naman yung naging assumption ni Bohr. Ang naging problem lang is, hindi niya nga kayang maipaliwanag at ang ginamit niya nga is just naikot lang yung electrons natin at hindi siya wave. So yun yung reason kung bakit nagkaroon siya ng mga shortcomings. Pero tama yung kanyang assumption that indeed the angular momentum is equal to nh bar or nh over 2 pi. Okay, so isa pa din complete na revolution na allowed. Okay, so yung revolution is allowed yung circumference niya. Okay, we can now see that the de Broglie relationship leads at once to this quantization condition. Okay, and lastly, class, we have the uncertainty principle. So we have what we call class the Gedanken experiments. Pag sinabing Gedanken experiments, class, yun yung mga experiments na hindi talaga kayang gawin sa lab. Pero you can readily investigate what would happen just by using your mind. So pwedeng imagination. Imagination lang talaga yung pwede. So very significant Gedanken experiment was carried out in 1926 by Heisenberg, who considered the procedures that would have to be followed in order to make a simultaneous measurement of the position and momentum of small particles such as an electron. So he realized that it would be impossible to make accurate measurements of both properties, since any technique for measuring one of them will necessarily disturb the system and will cause the measurement of the other one to be imprecise. Ano ba yung nangyari? For example, class, gusto mong malaman yung position sa spectrum nung iyong nung emission. So para makuha mo yung position niya, kailangan mapaliit mo, class, yung kanyang wavelength. Tama ba? Para magkaroon ka ng fine line. Kaya nga lang, class, ang problema is kapag masyadong maliit yung wavelength, masyadong mataas yung energy. And since directly dependent ang momentum sa energy, ibig sabihin sobrang laki ng momentum. Gets, class? So ibig sabihin, kapag gusto mong tingnan yung position, there would be a huge uncertainty in the momentum. So if you're going to look at the certainty of the momentum, there would be a huge uncertainty in the position. Kasi for example, gusto mong paliitin yung momentum, so palilitin mo yung energy, that would give you a huge wavelength. So masyado namang maliit yung iyong position, yung certainty sa position. So there is this uncertainty in the position, in the simultaneous calculation of the position and the momentum. So these conclusions are expressed in the Heisenberg uncertainty principle, or the principle of indeterminacy, which may be written as the uncertainty for the position times the uncertainty for the momentum, Q plus yung position and P yung momentum, is greater than or equal or almost equal to H over 4 pi or 1/2 ng ating H bar. Okay? So we have delta Q times delta U. Pwede din natin, class, tingnan kung ayaw mong momentum, gusto mong makita yung uncertainty sa position with respect to the uncertainty in the velocity, for example, pwede naman. But this time, syempre, kailangan natin i-convert yung U with respect to the momentum. So that would give us H over 4 pi times mass, or H bar over 2 times mass. Okay? Or pwede din natin, class, itingnan yung time. Since we know, class, that the change in time is just the change in position per unit velocity. Kung gusto mong malaman yung change in time, kailangan mo lang i-check yung naging change in position niya at yung kanyang velocity, right? So, because velocity is just your position per unit time. So, we have delta T is equal to delta Q over U. And delta E, class, is U times delta momentum. Tama ba? So, kung gusto mong malaman, class, yung energy, kailangan mo lang malaman yung momentum and yung U, or yung ating velocity. So given na meron siyang equation parehas, class, na may velocity, pwede nating i-take or tingnan yung magiging uncertainty kapag simultaneous tinignan natin yung time and yung energy. So we have energy and time uncertainty nila is equal to H over 4 pi, which is equal to 1/2 H bar. So this is just the same, class, as the uncertainty principle regarding the position and momentum. Got it? So if an electronic transition occurs from the ground state of an atom or molecule, the spectral line is sharp. Ito, class, yung nakikita sa mga spectrum. Kung galing daw, class, sa ground state yung molecule, sharp ang ating spectral line. Bakit, class? Kasi it covers only a narrow range of wavelengths. Tama ba? However, if an atom or molecule is in an electronically excited state, its lifetime may be very short. Maikli lang yung time, so maliit lang yung delta T natin, but delta E would be large. Tama ba? Kapag ka nasa ground state ka, class, you wouldn't know kung kailan siya magsisimula ng absorption. So malaki yung delta T. Pero maliit lang yung magiging maliit lang yung energy ng nasa ground state. Kapag naman nandun ka na sa excited state, mabilis lang class yung emission, pero napakalaki naman ng energy. So the energy of the transition therefore covers a range of values and hence the spectral line is broadened. So actually class tapos naman na tayo. So this this is the reason why meron quantum mechanics ng class, also the Heisenberg uncertainty principle ay kailangan natin for us to describe why the atomic theory of Bohr was faulty in a sense that he wasn't able to describe or to explain why certain lines are being fine and why certain lines are being broad. Got it? So yun yung isa sa mga problems, right, during the time of Bohr in his atomic theory. So the reason behind that is that there is this uncertainty in the simultaneous calculation for the change in energy and change in time. Also, that is also true for the change in position and the change in momentum. So yun lang class. Do you have any question regarding any of the three modules that we have discussed?